Hey guys, this is a video on solving ordinary differential equations using Laplace transforms. In this video, I'm going to be working what I like to call a type 2 problem, which just means that our characteristic polynomial has multiple identical roots. So let's go ahead and get started. The first thing I notice about this expression is that we are already in the Laplace domain because we have s as our variable. And the second thing I notice is that we are already in both normal and proper form. If you have any questions on normal and proper form, please go watch my overview video on this topic because I go into a lot more detail about normal and proper form in that video. So the first step to actually solving this problem is to determine the types of roots. So I'm going to rewrite my denominator. And this will help me see that I have two roots located at s equals -7 and I have one root here at s equals 0. So again, if I hadn't have told you that this was a type 2 problem, we would be able to tell that this was a type 2 problem based on these two identical roots right here. So our second step is expansion. So I'm going to go ahead and pick arbitrary letters to represent my numerators. And then for my first denominator, I'm going to have s. For my second denominator, I will have s plus 7. And for my third denominator, I will have s plus 7 squared. Step 3 is to find a common denominator, aka the characteristic polynomial. So my characteristic polynomial is this guy right here, which also matches this. And so basically what I want to do is multiply each of my fraction terms by something over something in order to get a common denominator on the right-hand side that also matches the denominator on the left-hand side. So for my first term, I'm going to multiply both the top and the bottom by s plus 7 times s plus 7. For my second term, I'm going to multiply by s times s plus 7 . And for my third term, I'm just going to multiply by s. Now I can take and combine all of the numerators on the right-hand side because they have a common denominator. A common denominator. Wow, I just can't say that word today. And now what I can do is set the numerators equal to each other because now both the left and the right-hand side have the same denominator. That does not look like a C. There we go. That looks better. Okay. So now I'm going to go ahead and expand out my right-hand side. Okay, and at this point we need to move on to step 4, which is equating the coefficients of S. So I'm going to move on to another slide for this step, if my mouse will let me click instead of just putting dots everywhere. There we go. Okay, so from the previous slide we had the following. Now, usually at this point, I like to take and add 0 coefficient terms to the left-hand side, just so that it makes it a little bit easier to see what all I have on the left and the right-hand side when I am equating the coefficients of S. So for this problem, I'm going to add a 0s squared and a 0s to the left-hand side, because as I equate the coefficients of S, I'm going to have my S squared terms, my S terms, and my 0th order terms. So now it's easier to see that for my S squared terms, I have 0 on the left-hand side and A plus B on the right-hand side. For my s terms, I have 0 on the left-hand side and 14a plus 7b plus c on the right-hand side. And then for my 0th order terms, I have 2 and 49a. Okay, so now I can move on to step 5, which is solving for the residues. So I'm going to go ahead and solve this equation. And I'm going to get a value for a. So a equals 2 over 49. And now I'm going to take and substitute this value for a back into my other two equations. So now that I've solved for my residues, I can go on to the last step, which is to substitute these values back into the partial fraction expansion and take the inverse Laplace transform. So, if you recall from 2 slides ago, the right-hand side of our partial fraction expansion looked like this. So now that we have solved for the values of a, b, and c, we can obtain the following. So now we can go to our Laplace tables, or our one-sided Laplace tables. And I usually use the Laplace tables in my textbook, or my professor gave us like another handout that had the Laplace tables. But basically, you can just Google any one-sided Laplace transform table and use that for this final step. So, looking at our one-sided Laplace transform table, we see that for this first term, if we pull the 2 over 49 out of the numerator, because it's just a constant, then in our Laplace table, we have something that looks like this. And so therefore, converting back to the time domain, we just get 2 over 49. Looking at this term, if we pull out the negative 2 over 49, we see something of this form in our Laplace table, and we can obtain the following. And last but not least, we do the exact same thing for the third term. Now we can take and obtain the complete solution in the time domain. Oops, there's supposed to be a T in front of that. And because we use the one-sided Laplace transforms, we are going to multiply this entire output expression by the unit step, which is u of t. And this is our answer. So that's it. I hope this video helped you guys better understand how to solve an ordinary differential equation using Laplace transforms.